For this lesson, we're going to find extrema on an interval. And extrema, it's just another word for extremes. We're looking at extreme maximums or extreme minimums, highest values of a function for the maximum, lowest value for the minimum, on a given interval. Let's talk about open and closed intervals first, just as a review, hopefully. We're talking about open interval. An open interval is where the endpoints are not included, and a closed interval, and we use parentheses for those. A closed interval is where we have these endpoints would be included, whatever those x and y values happen to be. Okay, so let's just talk about, just as an example here, let's say we have a graph that looks, I don't know, something like this, some sort of parabola or something. And I want to know the extremes between, say, this a value here and this b value over here. So here we're looking at, if I'm talking about the open interval, I'm talking about open interval AB. From here, if I extend this up and extend my other endpoint up, these are the endpoints of my interval. Don't draw very straight lines there, but okay, so if these values aren't included, we're not going to include this value here at A, and we're not going to include this value B because of the open interval status there. Okay, so if I want to look at then what my extrema would be, well, I would have right in this area here, this would be a minimum. Because that's the smallest value in that interval between A and B. I would not have a maximum because this appears to be the maximum, but since it's on an open interval, I'm never actually going to be able to reach that point because that point's not included. Whereas if we're looking at a closed interval, I don't know if I can reproduce that, but same idea. If I'm looking at a closed interval, let's say from A to B, where A and B would be included. Again, let's put A here. Let's put B over here somewhere. So A is going to go up and hit about right here. B would go up and hit somewhere up here. I would still have a minimum here at the trough, if you will, or the valley. And up here, since now this value of B is included, and it's higher up than my value of A over here, this would end up being a maximum over here at B. And again, if I'm talking about the maximum, I'm talking about how high that value is. So I'm looking at the y value. So f of B would be a maximum, and it would be located at B. Okay, let's talk a little bit about absolute versus relative extrema. Again, let's look at just some example here. Let's say I have some function, and it comes over here and it does one of these, and then maybe it does this, and then maybe it does this, and then maybe it comes down here. Let's make it go a little bit further. Okay, and I want to say, let's find the extrema, find the extremes on the closed interval. Again, we just use A and B as our endpoints. So A is down here, B is over here, okay. Now it's probably pretty easy to see that right up here we're going to have a maximum, and over here we're going to have a minimum. Okay, now we have these other parts where it looks like this is coming down to a minimum here and a maximum here. Now, not on the entire interval, okay, and that's where a relative extreme, is where, or a relative, either way, minimum or maximum, come from these hills and valleys. So since I have a hill over here on the left side, this would be considered a maximum, but it's a relative maximum. I mean, it's only in relation to everything. It's all relative. It's a maximum here in this general area, right there. Now, not on the entire interval. Over here, the other maximum we found a minute ago, this would be the absolute maximum. Absolute. Okay, that's the highest point in the whole interval, as opposed to this other one. Over here at B, this would be the absolute minimum. The absolute minimum down here at B. This would be a relative minimum over here at this valley. Okay, so all of our extrema, minimums or maximums, are going to occur at either a hill or a peak or in a valley. So either here, 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 hills and valleys, or at the endpoints. Endpoint here, endpoint here. One other thing, relative extrema are sometimes called local. If I'm looking for a local max or a local min, a local maximum or local minimum, we're talking about the relative max or the relative min. Okay, so this is just another term, another way you'll see it. And absolute are sometimes called global. That's supposed to be a quote there. Global. Global extrema. And is an absolute on the entire globe and the whole sphere, if you will, of this interval, as opposed to a local or a relative that's just in a certain area. Okay, so extrema are useful. They're helpful to us. They help us find different things about a graph and a curve. And we'll get into those later on in this chapter on what we do with them and why. But how do we find them? Well, relative extrema only occur at critical numbers. What's a critical number? Well, a critical number of a function is when the derivative equals 0. Those hills and valleys that we looked at a second ago, they're going to have a horizontal tangent, and a horizontal tangent we know has a slope of 0, and the slope of 0 is where the first derivative equals 0. Okay. Critical numbers also happen when our first derivative does not exist. Okay, so how do we find them? Okay, so here's our steps. If we want to find our extrema on a closed interval from A to B, first, find the critical numbers. Okay, so take your derivative, find where your derivative equals 0, or where your derivative does not exist. All of those will be critical numbers. Then we have to evaluate each critical number, evaluate the function at each of those critical numbers. So we'll plug each of those numbers in and find our f of x into the original function, not the derivative, into the function. Okay. We also are going to need to evaluate, and this is the step that people miss, evaluate f at each endpoint. If we're talking about a closed interval here, we also have to see at the endpoints, because we might have a whole bunch of critical numbers in between these interval endpoints, but A or B may give you a number higher or lower than any of those that we found in the middle. And lastly, well, once we evaluate all those, the least value is the minimum, the greatest value is the maximum. Okay, so let's do some. We're going to find the absolute extrema of h of x equals 5 minus x squared on this interval from -3 to 1. So, this is some parabola. It's going to open down. It's going to go, and we're looking at just the values between -3 and 1. When x is -3 until +1. So, first step, let's take our derivative so we can find our critical numbers. Derivative of h prime of x. If you want to pause that and do it on your own, hit pause now. So you should see that that is going to be a -2x. Okay, so now we need to evaluate, or first we need to set this equal to 0 and solve, because where our critical numbers are where our derivative equals 0, and you should be able to see that x equals 0 is a critical number. And I'm not going to be writing critical number always, but this just to show you there's a critical number. Okay, so that's where our derivative does not exist. If I look at this, -2x, I'm sorry, that's where our derivative equals 0. -2x, I don't have any x values where that exists. X is defined for, this derivative is defined for all values of x. I don't have any domain restrictions there at all, so we're fine. This is our only critical number at 0. So I'm going to need to evaluate my function at that critical number, also at the endpoints, at -3 and at +1. If you want to put this into a chart or a table, that's fine. But so this is going to be 5 minus -3 squared. Looks like -4. At h of 0, this is going to be 5 minus 0 squared, which is 5. And when h is 1, this is going to be 5 minus 1 squared is 4. Okay, now I'm looking for the absolute extrema. So, I've only got 3 values here. Well, what's our smallest value? -4. So, we would say that our minimum, we have a minimum of -4. It tells us what our minimum is. The y value is the what. And where does that happen? Well, when x is -3. The y value tells us what the minimum is. The x value tells us where it's located. So this is our what, and then the x value is the where. And that's critical. Okay, and we're talking about maximum and minimum. We're talking about how high or how low, so that's a y value. The -3 just tells us where that's located. And our largest value in here, our maximum, would be 5. So we're going to have a max of 5. Where does that occur? When x equals 0. Or at x equals 0. Okay, let's do another example. We're going to find the absolute extrema of this function here. I'm going to rewrite it. F of x equals 2x over this quantity, x squared plus 1, on this interval from -2 to +2. Okay, so first step, we got to find the derivative so we can find our critical numbers. Critical numbers are where that derivative equals 0 or doesn't exist. So, first step, find the derivative. If you want to pause this and do it on your own, that's a great idea. Good practice. Ready, go. Okay, so we're going to have this, we have a quotient here, a division problem. So we're going to have to use our quotient rule. Low, d high, minus high, d low. Derivative of x squared plus 1 would be 2x. All over low, low. x squared plus 1 quantity squared. If I simplify that on the top, looks like I'm going to get 2x squared plus 2, distributing that, minus 4x squared all over this quantity here, x squared plus 1 quantity squared. Okay, so if I take the numerator and set it equal to 0, that'll give me some critical numbers here, because this is going to equal 0 when the numerator is 0. 2x squared, where's my pointer? 2x squared minus 4x squared, negative 2x squared, plus 2 equals 0. So I would subtract 2, divide by negative 2, x squared would have to equal 1. And so x is going to be, take the square root, positive 1 or negative 1. There's two critical numbers, so I'm going to have to evaluate for both of those. And also, I need to evaluate where the first derivative does not exist. Well, it's going to not exist where the denominator equals 0, because values are undefined there. If I take the square root of both of those, I'm going to get x squared plus 1 equals 0. And if I subtract 1, x squared equals negative 1. Well, so I'm going to have no values there. This is not ever a non-existent, but we do need to check it, because I can't take the square root of a negative. So I don't have to worry about any other values there. Okay, so I've got my two critical numbers where I'm going to evaluate. I'm going to evaluate f of negative 1. I'm going to evaluate f of 1, two critical numbers. Also evaluate the endpoints. And f of 2. If you just plug these into this function into your calculator and look at the table, it's a lot quicker that way. Or, again, we're just going to plug this in right in here. So if I do this real quick, if I plug in negative 2, I'll have negative 4 over, I believe, 5. Negative 2 squared plus 1. For negative 1, I'll have negative 2 over negative 1 squared is 1 plus 1 is 2, or negative 1. If I plug in positive 1, I'm going to have positive 2 over 1 squared plus 1 is 2, which is positive 1. And if I plug in 2, I'm going to get 4 over 2 squared is 4, 5. Okay. So, now we just need to determine what's our minimum, what's our maximum. Here's our min. This is going to have a minimum of negative 1. Our maximum, our biggest value is here. So we're going to have a maximum of 1. Our minimum occurs at negative 1, 1, and our maximum occurs at positive 1, 1. Okay, here's your assignment. Try some of those on page 167, 1 through 5 odd, 17 to 35 odd, and 52 to 58. I want you to do all of those. A lot of those you aren't actually finding any extrema. You're just looking at a graph and trying to figure out if they exist or not on the open interval. And we'll see you this week.